Hello and welcome to this training session at the Education Designers Lighting Forum. Today's topic is going to be navigating the future, code compliance and energy efficiency, presented by me, Sean Lafferty, President and CEO of Steinel America. Your learning objectives for today. At the end of this course, participants will be able to, first off, understand the importance and the significance of energy codes. Should also be able to evaluate the key capabilities of lighting control systems that are featured in the most common and the most advanced energy codes. Attendees should understand the variety of applications that require lighting control systems to meet energy code. And finally, attendees should be able to design lighting and controls to minimize energy consumption, delivering a positive return on investment using cost-effective solutions. So I want to start off with a challenge question. What if you understood the most advanced energy codes in the simplest of terms and could use them to improve the energy efficiency of the built environment all around us? Let's start with, why do we even have energy codes? Where do they come from? The first energy codes were introduced in the US about 40 years ago, a little over 40 years ago in 1983, in what was then called the Model Energy Code. Uh, why we have the energy codes was a variety of things. And really, it's to encourage the adoption of best practices that reduce energy consumption in the built environment. What are some of those benefits that come from using those best practices? Well, there's the environmental concern, reducing greenhouse gas emissions by requiring less carbon emitting electricity production, national security by reducing reliance on foreign fossil fuels, resilience by reducing the loads and impact of electricity supply disruptions from weather or other forces majeure, and sustainability of the grid, very important to minimize the need for building out new energy infrastructure, as we try to satisfy the continued growth in commercial and industrial construction, new factories, new offices, new buildings going up, new schools going up, new healthcare facilities, et cetera, all needing more power. And also the trend in the adoption of some very intense electricity consuming technologies, both in home heating, office heating, electric vehicles, and the like. So the grid is really under a lot of pressure, and the energy code can help us reduce that pressure. And then finally, most relevant for, I think, most of our customers is the cost savings and the property values. That if we can reduce the operating cost for the eventual tenant, that's just a bonus. That's value add for the tenant moving in, as well as the property owner who might be renting that space. So lots of benefits as to why we have energy codes. The importance of this is really critical. And we focus here in today's discussion on the commercial and industrial built environment. And the reason being, this is according to the U.S. Energy Information Administration. You can see all the different sources of energy and where those sources of energy go. Of course, the biggest portion across the top is petroleum in the transportation segment. But if you look at what is turning into electricity via natural gas, some renewable sources, but we still have a significant amount of coal and a growing amount of nuclear, or regrowing amount of nuclear. The power sector is distributing 62% of its energy that it puts out goes to industrial and commercial applications. And that's 36% of all energy uses. That includes oil used in cars and trucks on the roads and in airplanes. So, across all segments of all energy consumption, it's 36% of all energy, and commercial and industrial represents 62% of the electricity coming from the grid. So this is a really big opportunity to make a big impact to reduce energy consumption, and of course help the US and 139 other companies achieve net zero emissions by 2050. Energy codes have been in place, like I said, for quite a long time. And, in the last several years, with the advent of LED lighting and the digitalization of lighting, lighting controls have really become front and center as part of the energy code. And you can see in this map, you can see the level of intensity of the energy codes across the country. The darker the green, the more intense the energy codes. So, IECC 2021 and Title 24 are some of the most, some examples of some of the most advanced energy codes, on down to IECC 2018, IECC 2015, where there's a lot less. And of course, and there are still a number of jurisdictions where there's either no energy code or the energy codes are pretty old, 2009 and 2012, that don't really take advantage of a lot of the technology that's been rolled out over the last 10 years. So, but we are seeing that the overwhelming majority of states have an energy code, and a growing portion of those have advanced energy codes. So it's constantly changing. It's constantly getting finer and finer, and we're finding new and better ways to enhance the energy code to drive more energy savings as they get adopted, as the codes get adopted more and more across the country. So in the simplest of terms, how is the energy code constructed? If you try to read the ASHRAE code, the IECC 2021 and proposed changes for 2024, the New York City Energy Code, the Title 24 documentation, you're talking about thousands and thousands of pages of very detailed specifications on how everything needs to be done. We're not going to try to cover all of that here, but at the highest level, basically what we're talking about is there are some key capabilities that lighting control solutions provide today. Those things include things like how we turn the lights on, occupant sensing shutoff, automatic scheduling, manual control, daylight control, institutional tuning, receptacle control, and demand responsive control. And we'll talk more about what each of those capabilities really is. But if we take those key capabilities on things you can do because we have the technology to do them, we then cross that across a variety of applications. And there are long lists of the various types of applications that each of the energy codes addresses: hotels, motels, industrial manufacturing, libraries, healthcare facilities, parking garages, restaurants, retail stores, schools, office buildings. And then within those, inside of an office building, there are specific requirements for each different type of space inside the office building. For example, like corridors, common spaces, private offices, open offices, and meeting rooms. So the energy code is really just a function of how do we expect designers and builders to take these key capabilities that can drive energy savings and apply them in these various applications. So what are the key capabilities? First and foremost is turning the lights on. And there are a variety of ways we can have lights come on, but lighting control systems typically include a combination of automatic and manual means to turn the lights on. Automatic methods might include things like occupant sensing or time scheduling. In many places, there's vacancy mode, which requires that the user turn the lights on manually. And we also typically want some form of manual user override. So there's lots of different ways we can turn the lights on. Um, Occupant sensing shutoff. So once we recognize that there is no occupancy, we may want to turn off all or part of the lighting load once the area is vacated of occupants. So, and typically in those cases, once the occupancy is restored, we want to restore some either all or part of that lighting load. So that's another technology that we have available to us. Automatic scheduling control. It's a time-based lighting control system that is capable of being programmed to control the lighting based on the time of day. So we may have some requirements that are different in certain spaces when a facility is open versus closed, whether it's a holiday or a work day. There are different ways we might consider using sequences of operations that can change the basic programming. That after hours may not mean the lights are off, it just may mean they come on at a different level. But we may want to have some scheduling that is going to allow us to change the way the lights behave in order to maximize energy savings based on usage. Manual control. And this is an important one because it allows the occupant to override the automatic controls that might include occupant sensing, automatic scheduling, for example. So this allows people to turn the lights on, shut the lights off, and dim the lights. So if something, the time clock automatically shuts off the lights, perhaps we want to allow the user to go and turn the lights back on, for example. Daylighting control. This is a big one, and it adjusts the luminous flux of the electrical lighting system in response to available daylight. this kind of control that uses one or more photo sensors to detect changes in the daylight levels and automatically adjust the light levels in response. And there are lots of changes over. This is one of the areas of focus really over the last 6 to 8 years of increasing the amount of daylighting control and the restrictions and requirements around that, which we'll talk about in a minute. Institutional tuning. Institutional tuning is the process of adjusting the maximum light output of a lighting system to support the visual needs and or save energy. This control strategy is implemented at the institutional level, not at the user level. The maximum light level is typically can only be adjusted by authorized personnel. So this is where we may have a luminaire that provides more light than is required for the expected task of the workspace, for example. And so we cap that at some percentage where the end user can only dim the lights upwards to a certain light level, thereby limiting how much energy they can possibly consume. Receptacle control. This is a hot button topic. This is the ability to control automatic shut off of receptacles when a space is unoccupied, either at the receptacle or circuit level. And this is one I'd really like to dive into a little deeper before we get into the later part of the presentation. I just want to take a little side note here on the return on investment of receptacle control. I think this is a topic that was very, very relevant, 10 or 15 years ago. But I think other legislation and changes in technology have really minimized the effect of this. I think the idea of receptacle control was to control what is called a vampire load or a latent load or a standby load. And basically, this is when you don't use your laptop, but you leave it plugged in overnight, or a phone charger plugged in, or a monitor plugged in when there's nobody there. And the real issue on this is there are now requirements in these types of devices to minimize the amount of standby load. And so the current standby loads, and I took these averages from Science Daily on what the average vampire load of some of these technologies is. And if you look at how many hours there are available, if you have a 8 to 6 p.m. work week from Monday through Friday, the total hours that you would have where either the automatic schedule would shut off the lights automatically would give you about 5,336 hours of having that load shut off, which results on an annualized basis of just a couple of dollars for laptops, phone chargers, monitors, and printers. The one exception is, of course, space heaters, which in many cases are generally not allowed, but still people behaviorally like to bring them in if they don't like the temperature control in their office. And if that gets left on at 1,500 watts, well, now we've got a significant cost savings. And an occupant-based shut-off, we're also turning the lights off when people vacate their desks. So, recent article by Science Daily showed that the typical worker was only at their desk for 5 hours, 41 minutes per day. If you factor in a 20-minute shut-off, that's roughly 6 hours, 5 times a week, so only 30 work hours. But in any case, over the course of a year, you get more savings. But again, aside from the case example where you have a space heater plugged into those, really the ROI of receptacle control is minimal. The return is very, very small. Lastly, I want to getting back to the key capabilities, demand responsive control. Demand responsive control, the most common along the West Coast in California. There's some the utilities in the Northeast also have similar types of programs, but this is when there is a short-term requirement by the utility to reduce consumption. Companies may agree or be required in certain jurisdictions to cut down the amount of energy they're using at moments of critical peak load. So the demand response is another critical capability of the energy code. So, the applications, I mentioned a few of the top applications. I won't go over this whole list, but there are lots of different environments that have very specific energy codes. I took this list. This list is actually published in the table of contents for California Title 24. I thought it was a good representative list of all the variety of different spaces that have different applications, different use scenarios, and therefore we would want to use the different types of technologies differently for each of these. But I'd like to focus a little bit on primarily offices, really, and the different types of spaces, right, that there are in offices, corridors, common spaces, private offices, etc. We'll go through some of these case examples one by one here. But first, I want to just kind of summarize. So here's a summary table, and as simply as possible. And again, these energy codes are literally thousands of pages each. So I've just tried to distill this out to the most salient nuggets here. IECC 2021, in fact, across the board, turning the lights on the draft version of IECC 2024, Title 24, and the New York City Energy Code all require either automatic full-on with occupancy sensing. They all require for corridors, full on with occupancy sensing. Shut off, you can see there's, for the most part, partial off to 50% or some other lower maximum with a maximum 20-minute time delay. And that's for most of the energy codes. New York City, the time delay maximum is only 15 minutes, so a little bit more aggressive and just slightly different from the others with a full off required there. Automatic scheduling, they're for corridors, not required in most of the energy codes, but in Title 24. If we're doing partial off to 50% with using sensors, using occupancy sensors, we can do after hours with scheduling. So we are allowed to use automatic scheduling for after hours in Title 24 for California. Manual control, some jurisdictions, the new IECC 2024 and the New York City Energy Code require that we provide manual control for corridors. IECC 2021 and Title 24 do not require that we have a manual user override for the corridor. Daylighting control. If we have a control, the big difference here is how many watts are in a daylight zone. Typically, most corridors do not have daylighting zones because there's not typically windows. There are usually walls on either side of the corridor. But in the event that you have a corridor that runs along an exposed wall with daylight available, it comes down to what is the wattage in the daylight zone. And you can see the variety there. IECC 2021 is looking at changing that from 150 watts down to 75 watts. Title 24 is at 120. And for New York City, we're already at a relatively low 100 watts for that. And for corridors, there's no receptacle control required. I want to go over, as we take a look at some specific applications, I want to look at two very common approaches. There are lots of other approaches as well, but we're looking at two of the most popular ways that you can solve for the energy code. One, I like to call the all-inclusive approach. And this is where you have a controller, it's typically a 3-zone controller, maybe extendable. And for the analysis that we're going to show here, we are extendable. We can add relays to that up to 8. There would be a time clock included in the controller, very simple communication by 2-wire, for data and power. We have 0 to 10 volt dimming capabilities for each of the 3 to 8 zones, and we have the capability to do multi-zone daylight harvesting. So these are all included in your basic controller. And with some of these systems, you also have sensors that have very high coverage patterns. So we're going to optimize here and use the sensors that have the biggest coverage patterns that still meet the energy code requirements. And we're also going to include a daylight sensor in those sensors. These are very common types of capabilities of what I would call an all-inclusive solution, without specifically naming any brands. The second version we're going to look at another kind of solution. It's going to be wired, but it's going to be a series of single zone controllers. They're each connected by a Cat5 or Cat6 cable for data and power. Each will be able to control 0 to 10 volt dimming for one zone. So for each zone, we will have an independent controller. And we're going to use sensors here that are also standalone in the sense that they just provide occupancy or vacancy data. Typical coverage pattern is a 12-foot radius. That's the most common in the industry. Uses a lens that was designed by a gentleman named Clater, the Clater lens. It's very commonly used in both passive infrared and dual tech sensors. We're going to require a separate standalone daylight sensor. So rather than have that included, we'll only have that added as necessary. And lastly, we're going to need potentially a receptacle controller in certain environments. So on the left-hand side, you've got the all-inclusive, everything's in there with high coverage sensors. On the right-hand side, you've got lots of different pieces and parts that can be specified by the engineer, specific to meet exact energy code requirements with no extra pieces and parts, and what I would like to call the Lego kit. Okay, so going back to that corridor, we've got here a typical office layout. You've got a central corridor here and a corridor down on this end. And basically what we've got here in the all-inclusive solution, we've got 6 components. We've got 1 digital controller. We've got 1, 2, 3, 4 photo cells, and we've got a couple of extra, 1 extra relay here. So the total cost on this side, we've determined or estimated that the material cost is going to be about $1,292, and the labor cost, we just used a simple, just to keep things simple, we rounded off at $50 per component in the solution. So that's assuming is roughly $100 an hour fee rate for that installer, and having them be able to put in 2 components per hour. So because they are located in various places throughout the space, so it requires a little bit of moving around and doing the install work. Based on the right-hand side in the Lego solution, we've got 12 different components, and the material cost ends up coming out to be quite a bit higher with the more pieces and parts, and the labor cost therefore also goes up with that. So in this particular solution, you've got more sensors. It's really what's driving it is we've got a photo cell down in the daylighting zone here in the lower left. 1, 2, 3, 4, 5, 6, 7 sensors required to cover the corridors, and 1, 2, 3, 4 power packs to control the switch legs, so single zone controllers. So it ends up being a total of 12 pieces that need to be installed with a labor cost that's probably about double what it would have been on the left-hand side. Based on our calculations, we were looking at occupancy-based shut-off, daylight harvesting in the lower left corner. We're using the New York City, most recently published data for New York City was roughly 16 cents per kilowatt hour for commercial applications. And we see this solution, both solutions able to deliver 3,916 kilowatt hours of savings annually, which gives us a $618 savings. So that's nice, good for the environment, good for the bottom line on both sides. Just the slight difference on the left-hand side, you can see there's a 2.6-year payback, and on the right-hand side, you can see there's a 4.2-year payback. So having the fewer pieces all included to meet the code proves to be a little bit more efficient. But either way, we're getting really good return on investment here. Good solution. For the lobbies, code requirements, again, across the board, turning lights on. We want automatic full in a public space like a lobby. So occupancy sensing shutoff. Again, we're at 20 minutes for the major energy codes. New York City energy code, a little bit more aggressive. Automatic scheduling, not required in any of these applications, nor is manual control, except for New York City, where you need to have a switch for someone to be able to manually override the automatic settings. Daylighting control, again, same story as the corridor. Depends on the load, with the varying loads per jurisdiction. And receptacle control, interestingly, for IECC 2021, the proposed 2024, and New York City, there are no requirements for receptacle control. However, in the Title 24 Energy Code, there actually is a requirement in lobbies that all the receptacles need to be controlled, at least 50% of them, if they're 15 or 20 amps, with a max occupancy-based 20-minute timeout or time clock with a 2-hour override. Restrooms, of course, in public spaces exempt, but the lobby is, of course, not a restroom. Okay, so on the left-hand side, we have our solution. We have two multi-zone controllers, and we have two occupancy sensors covering the entire space. We have enough lighting loads there that we need the extra relays. On the right-hand side, we've got 8 components. We can see 1, 2, 3, 4, 5, 6 total switch legs, which means 6 power packs, 6 single zone controllers. And we've got 2 occupancy sensors here as well. Based on occupancy-based shutoff, we are generating about 2,245 kilowatt hours annually of energy savings in these common spaces for a smaller return on investment of just $354. We have slightly fewer components here, but we do have those 2 big controllers and 2 aux sensors. So we have a very comparable price point. We have a slightly less labor since there's just a couple less items here, but for the most part, we've got a fairly similar, reasonable payback, 4.2 years, 4.7 years. So pretty good return. Not as good as the corridor scenario. Break rooms. So in the office, in a break room, you got now we can go manual or partial. We can go manual on or partial on to 50% in most jurisdictions. In New York City, it is manual on only. Occupancy sensing shutoff. We're at 20 minutes again, except for New York City, it's 15. Daylighting control, you're going to see this is going to be pretty much the same for most spaces across the board. And receptacle control, now we have every jurisdiction requiring receptacle control in the break room. Very important. So we look at this little kitchenette area, and we have a bank of wall switches here, 4 wall switches in either solution. Then we have a pair of occupancy sensors, another wall switch here, and a wall switch here. We've got an occupancy sensor here. We've got a daylighting zone here. And then we've got the 2 3-zone controllers with an extra relay attached. And we can use the standard relays in these devices for receptacle control as well as lighting load, since we've assumed they're 20 amp rated. On the right-hand side, we see the Lego-based solution, so pieces and parts, 1, 2, 3, 4, wall switches, 5 and 6, same exact configuration as the other scenario. The space is, relatively uniquely shaped and small, so again, 3 occupancy sensors. We've got a daylight sensor here. And let's see, we've got 1, 2, 3, 4, 5, 6 switch loads, as well as a plug load controller here, a receptacle controller for the plug load. So on the left-hand side, we're able to do this with 16 components. On the right, it's 22. And again, for these spaces, we're seeing a much lower return on investment here. We're now up over 7 years on this kind of an application. There just isn't that much energy savings to be had here. And as you can see, quite a bit of equipment on both sides of the ledger. That receptacle control is really not adding a lot of dollars to our return here. So we are cutting 3,000 kilowatt hours annually. That's great. Total energy savings dollar-wise of $475. That's nice. But at 7+ years of return, somewhere between the receptacle control and the requirement for daylight harvesting, we probably didn't make the return on investment here because of those 2 items. But any case, it is what it is. That's the code requirement. All right, let's talk about private offices. IECC 2021, 2024, Title 24, again, we have the option for manual on or partial on to 50%. In Title 24, we can, in certain cases, come up higher. And for New York City Energy Code, manual on only if we're under 200 square feet. If the private office is over 200 square feet, then we can do partial on to 50%. Now, 20 by 10 is a pretty substantial private office. And most applications are probably going to be a little bit smaller than that. But nevertheless, there is that provision for larger private offices. I guess there are a lot of executives in New York City. So Occupancy-based sensing shut off again, 20 minutes across the board, except for New York where it's 15. Automatic scheduling not required for private offices. Manual control, yes, of course. Everybody wants to be able to turn the lights on or off in their private office. And daylighting control, same as before. Receptacle control, same as before. We're going to have at least 50% of them on an occupancy-based sensor or occupancy basis or on a time clock. So in the all-inclusive solution on the left, you can see we've got some plug load control requirements. We've got two 3-zone controllers that are controlling those plug loads. No additional extra relays required here. We have those 2 plug loads plus 3 lighting loads, 3 wall stations, and each of those spaces has its own occupancy sensor. On the right-hand side, we are looking at something very similar where we have a receptacle controller and a plug load controller in each space. So we have 6 different components where we had 2 on the other side. We've got 1, 2, 3 wall stations and 1, 2, 3 occupancy sensors. So occupancy sensors and wall stations the same, just fewer pieces and parts in the all-inclusive, few more in the Lego. Price point on the material cost is roughly the same, and there's a slight increase in the labor amount there. So what we end up seeing here is a 5+ year payback, so not bad. Again, I might advocate that the plug load is probably not contributing very well to that payback period. But we are generating 2,650 kilowatt hours annually, which is great for the environment. We're happy to see that. And $418 going into the pockets of our tenants and or landlords. So again, creating value, but probably not as much, probably primarily really from the schedule-based control and occupancy-based control. All right, I think we've just got 1 or 2 more examples here. On the open office spaces, IECC 2021, 2024, Title 24 in New York City Energy Code. Obviously, the big thing that was introduced nationally and in Title 24 in 2021 was the cap on the amount of space being only 600 square feet. So this provides more granular control, allows you to turn off lights in spaces where if you've got a large open area and only one person sitting in it, only the lights in their area are required to be on. There will be some possible changes to that, neighbor spaces in 2024. However, the maximum controlled space now is 600 square feet, which, with a 12-foot radius, uh, is certainly smaller than 600 square feet on your typical sensor, and even on your large footprint sensor, you're still looking at roughly a 26 by 26, which is almost exactly 600 square feet. So 600 square feet is actually a fairly sizable space. Okay, on the occupancy sensing shutoff, again, we're 20 minutes or 15 at the end. It's interesting, you are allowed to use the time clock as opposed to occupancy-based sensing in IECC 2021 and 2024, not in Title 24 or New York City. Manual control, it's required that if you're using the for occupancy sensors or for the time clock, you have to be able to go and turn the lights back on. And for the time clock, you have a 2-hour override. So if the user gets up, walks across the room and presses the button, then the time clock will be disengaged for 2 hours, at which point it will then resume control of the space. Daylighting control, again, same as before, and receptacle control, again, same as the other applications. So in a larger office space, we decided to go with something that was essentially a 600 square foot space. On the left-hand side, we've got one occupancy sensor. We've got a primary daylighting zone and a secondary daylighting zone. So we're looking at the switch legs in these, and you can see that there are 4 2x4 fixtures, which is comfortably going to get us over the New York City requirement of 100 watts controlled in that primary zone, as well as in the secondary zone. So we have full daylighting control requirements. On the left-hand side, we've got one 3-zone controller, which is covering the switch slag and the plug load. We've got one occupancy sensor, which is able to be programmed to basically manage the daylighting zone in both the primary and the secondary through programming logic in the controller, as well as the daylight sensor for the primary zone and the wall station on the lower left. On the right-hand side, the Lego-based solution, we've got two lighting loads being controlled by 2 different power packs and a plug load controller for the receptacles. We've got 2 daylight sensors, one for each zone, and we've got 2 occupancy sensors to cover the 600 square feet effectively. So we wind up with 9 components, a little bit more expensive bill of materials, and a slightly more expensive labor cost. But nevertheless, in both of these cases, we've got terrific paybacks. Well, good paybacks, I should say, of 2.5 to 3.3 years. We're generating over 3,000 kilowatt hours annually of energy savings, with really just very little equipment to have to do it. So this is a no-brainer of a space that we should really be driving energy solutions and through lighting control. And the last example I'll give today, open meeting rooms. So in open meeting rooms, or common meeting rooms, you've got IECC 2021 and 2024 allow for manual on or partial on to 50%. Title 24, automatic full on with occupancy. So if you walk into a conference room, it should turn on. And New York City Energy Code, you must turn on the lights when you walk into a conference room. Occupancy sensing shutoff, we're again 20 minutes, except for in New York, it's 15. No automatic scheduling required. Manual control is required in every one of these cases. Daylighting, again, the same restrictions. So for New York City, 100 watts controlled. And of course, the time clock, the same restrictions that, yes, we have to control the receptacles in the meeting rooms as well. Okay, so here we have on the left and right our all-inclusive solution and Lego solution. On the left-hand side, we've got a daylighting zone here where we've got this string of fixtures, and these are going to get us, with these 4 fixtures, they will get us up to 100 watts. So we have to put the daylighting controls in. We have a daylight sensor for that. We've got an occupancy sensor on the drawing here that allows us to see the whole space. We've got a 3-zone controller extended by 2 up to 5 circuits. That's to cover the 4 zones of 4 different circuits of lighting loads. And we've got a wall station here. We've got 2 different wall stations because we've got 2 different daylighting zones. In the solution on the left, we can connect those up to the same controller and control all 4 zones. And we've got a plug load controller here on the right. On the left, we do not need a plug load controller. Total cost of implementing these solutions is actually relatively close to the same. So we've got a very similar bill of materials, very similar labor costs. Bill of materials on the left, slightly more expensive with that 3-zone controller and 2 additional relays. So we come in a little bit more expensive here than on the right with the 4 power packs and a receptacle controller. However, we do also have roughly the same payback of about 5.4 or 5.6 years. So that's based on a total energy savings of $301. A lot of these meeting room spaces, to be honest, they're not even, this is in the case that they would be used during all business hours. And if they're used even less than that, we would get slightly more energy savings. But for the sake of consistency in our assumptions, this is an application where perhaps, the payback is good enough, not great. So I want to leave you with 3 bold predictions. First and foremost, time clocks are dead. I just don't see how we're going to continue to use time clocks. I think the paybacks on some of the instances were not nearly as good as the occupant sensing paybacks, first and foremost. And with all the hybrid work environments, I don't know that we're ever going to get back to having, highly occupied office environments, whereby the time clock will be equally effective as the occupancy sensing. So we see just increasingly as we rely more and more on the occupancy control, time clocks are going away. Space heaters, if they're not outlawed already, should be outlawed. To be honest, I think it is typically in many jurisdictions, it's an OSHA violation to bring a space heater into a workspace. And honestly, if it's not for the space heaters under people's desks that are somewhat not supposed to be there anyway, we really don't need receptacle control at this point. I think the vampire loads are no longer an issue worthy of our time and attention and cost. And then lastly, I think the integration of lighting controls is really going to create more opportunities for bigger cost savings in HVAC and shades. I think the efficiency of LED lighting has driven us to the point where the ROI on lighting controls is in many cases marginal. In some cases, it's still quite good, but in some cases, it's fairly marginal. But if you could add that to HVAC control, occupancy-based HVAC control, and schedule-based control and daylighting control, all those things together, if we're doing that with HVAC and shades and cooling spaces by bringing the shades down in the summertime, reducing the HVAC load, that's really going to have a higher ROI than even the lighting at all. So with that, we'll open the floor to whatever questions anybody might have.